you very much for the introduction. And also, before I start, I want to thank the organizers for inviting me and giving me the chance and opportunity to talk today. And of course, I also want to thank the collaborators, which are David Hunger's group at the KIT and Olivier Assissé in Grenoble. And you see already the title of my talk. So in the next 30 minutes, I want to talk about something which is a little bit off topic and a little bit different background to the talks compared to what I heard so far. So I want to talk about nanoscale sensing, especially sensing of strain with single spins and diamond. And I think everyone would agree that it would be pretty amazing if we would have a sensor, a very tiny, small sensor, which is very sensitive to different kinds of field, especially strain, to, for example, create images of volumetric changes of thin layers or films and all the kind of stuff. And actually, these single spins and diamonds, namely NV centers, nitrogen-vacancy centers, give this opportunity. And that's what I want to focus in this talk. So these nitrogen-vacancy centers are point defects in diamond, and they have different kind of application. So one is nanoscale metrology, the focus of the talk, but beside that, it's also quantum computation, quantum communication. So the application side is very broad, but I just want to focus here. So this NV center is a spin system, a point defect. So obviously we can sense magnetic fields. Here I did some cherry picking of some recent experiments in this field. For example, an experiment by Marcel from Paris Sud. He did with his group domain wall imaging, just by sensing the stray field of the domain walls, in this case Bloch walls, but also Neal walls, and was able to create two-dimensional images. And here it's these typical tip-type setup. So the NV center, one single spin here is sitting in the tip of made out of diamond, and then he scratches over the surface and creates this two-dimensional image. And beside that, also another experiment from Patrick Maletinsky in Basel. He did an image of superconducting vortices in Qubit superconductor. Also same kind of principle, just scratching over the surface and detecting a stray field. And then, of course, you could also do with shallow NV centers very close to the surface, NMR-type experiments, and many more. But beside that, the NV center is also sensitive to electric fields. So you could do electric stray field sensing of large electrodes down to single electrons, which are close to the NV center. And then, since the diamond, this NV center is in diamond, you could also sense temperature, so thermometry could be possible. Either bulk sensing or even a little more biomedicine application would be if you have nano diamonds, so powder of diamond with NV centers inside, you could implement these in living cells. This has been done by the Fukami group. And then measure the temperature of the cell, of a living cell. It's also a beautiful experiment. And then, last but not least, strain sensing and spin hybrid systems. There are different kind of geometries which allow you to sense very sensitively and locally the strain. And this will be the focus today so basically strain sensing. So since the background is a little different and the NV center is very important, I want to sacrifice a few minutes to introduce this nitrogen-vacancy center in diamond so that you understand the fundamental principle, how the sensing really works. I'm pretty sure all of you heard of it more or less in a different kind of way, but just a reminder would be great, I guess. So that's the NV center. So it consists of a substitution nitrogen atom in a diamond lattice with a next near vacancy defect. So that's a point defect. It has a C3V point group, quite obvious if we just look at it. And usually it exists in different kind of charge states. So just by taking care for the valence electrons of nitrogen and carbon, it would be count 5 electrons, but the NV center is also kind of trap for electrons from the environment so that we can have 6 electrons. This is called the negative NV center. And during the rest of the talk, I will also only talk about this negatively charged NV center because this center is the one with these nice sensing properties. And so we have 4 orbitals, as in this case, dangling bonds in a tight binding picture. And if we do the group theoretical approach and linearly combine those, we get, in the end, 4 different kind of orbitals, the eigenbases, and we have 6 electrons, 4 orbitals, which means we have a 2-hole picture. And this counts then to a spin equal 1. So we have a triplet system. And that's basically the energy level scheme we have. So we have just a classical triplet system, ground state here, plus minus sublevels are degenerate in the zero field. And we have an excited state here, same principle, triplet. But also, since we are in a diamond, have the lattice around, and a spin-orbit mediated interaction also leads to a singlet configuration with S equal 0. So this is done by then intersystem crossing, where due to spin-orbit interaction, a phonon is emitted. And this 0 phonon line, which is really the line where no phonon is involved, just the electronic transition from the excited to the ground state, or inversely, is in the energy region of 638 nanometers, so in the red visible range, or if you want to take care for the electron volts, it's around 2 electron volts. And now there are different kind of decay paths illustrated by the arrows. So ms equals 0 has a very strong optical decay and a very weak intersystem crossing, highlighted by the different thickness of the arrows. And the plus minus sublevels have a very strong intersystem crossing, and the arrows are gray because these transitions are non-radiative. So this singlet state is also considered as a dark state. So here we don't get photons, only with this optical. Because this is very important for the qubit control. So far, we know now what the NV center is, and now we want to use this 2-level system to control and sense something. And therefore, we want to use a qubit or a 2-level system, which then accumulates phase with the sensing field, and we can then measure this. So here in this NV center, we have different kind of qubit configurations available. So we have the ms equals 0 state with the ms plus minus 1, for example, in the ground state or excited state. We have also then, if we split plus minus 1, those 2 states as a qubit configuration. And then if we include even hyperfine interaction with nucleus in the next near neighbor, we could also have the nuclear hyperfine states involved. But I won't talk about these. I just want to focus on the electronic configuration and explicitly only on the ground state here. Because the disadvantage of the excited state is, of course, the lifetime, the finite lifetime, which is in the order of 10 nanoseconds here. So very important for sensing is that we can always initialize our systems in the same state so that we know our starting point, and then we can start sensing from this. And this is, in our case, spin polarization into this ms equal 0 state. It's just because of these couplings with the singlet state and this dominating radiative transition between ms equals 0, because those optical transitions are spin selective. So I forgot to mention, only ms0 to ms0 is allowed, and ms plus minus 1 to plus minus 1 is allowed. So if you do the math and just follow one excitation from ms0 up here, it has a high probability to go down again to ms0, but if we start here and go up, it has a higher probability to go through this dark state and end up in the end also with a higher probability here. So that's the spin polarization we can exploit. And the yield is easily above 85% and can go, if you put in a little more effort, up to 96, 98%. So that's the yield. And we can exploit the same mechanism for readout this spin. Because now we know, okay, we can initialize the system. Now we want to get out the information from this sensing of the fields. And that's done by spin detection via the fluorescent intensity. So we just detect the photons emitted from the NV center. And in case we are in ms equal 0, we have a strong optical decay path. And in case of plus minus 1, due to this intersystem coupling and intercrossing here, which are non-radiative, we have a dark state. So just by counting the photons, we see, okay, we count less photons here compared to the bright here. And the contrast ratio can go up to 20%, or a little more realistic would be 10 to 15%. And we can really see this in this ESR type experiment. So it's just that we apply a microwave externally and sweep the frequency. And once we hit the resonance frequency of our state, we transfer population from zero, so the initialization, up to ±1 in the excited state. So here is the resonance frequency, 1.4 gigahertz. And we clearly see how the count rate just drops. So it gets darker. And the same for the ground state at 2.87 gigahertz. And then we nicely can see, okay, the spin has been in this state or in the other state. So the general measurement principle is always the same. We have an initialization just by irradiating it with a laser in the green region. Then we have time for manipulating or let it interact with a field to accumulate phase. And in the end, we can then read out the system again with the laser and look whether it's dark or bright. And then we know, okay, we were in one or the other state. And this is just an image, cartoonic image, how the experiment usually looks like. It's just a fluorescence microscope type of setup. We excite the system with a green laser, so we excite it off-resonantly. And then, here's our diamond sample. We have an objective to really focus, and with that we are able to address just one single spin. So one point defect is enough already to get enough signal to see and sense. That's also very interesting. We don't need many spins. One could be enough. Of course, we have some advantages if we look at more spins, but it would be possible. And then a microwave antenna just for apply the ODMR or ESR. And here then, by this dichroic mirror, we can just separate the input and output signal and go to the detector and count or look at the spectrum. So that's possible. So far, now the NV center was only under zero field conditions, and now I wanted to introduce perturbation so that we sense finally fields. And this is the ground state Hamiltonian. As I said at the beginning, I just want to focus on the ground state, though the excited state Hamiltonian looks at room temperature quite comparable qualitatively. So far, we are only at room temperatures, I forgot to mention, so no temperatures are needed at this point. So we have the zero field splitting, which is for the ground state 2.87 gigahertz. Then we have just a typical classical Zeeman splitting by an external magnetic field. So we lift the degeneracy of our plus-minus state. And the coupling here is 2.8 megahertz per Gauss. And now comes the strain. But before, maybe just to illustrate you a measurement we did to see that the Zeeman splitting really exists in the NV center. So that's basically the orientation. So Z is parallel to the symmetry axis of the NV axis. And in the diamond lattice, we have 4 possible orientations of our NV center, ignoring the sign. So depending on the orientation of the B field with respect to the to the symmetry axis of the NV, we have either a strong Zeeman splitting or none at all. And here you see we aligned the magnetic field in the way that some NV centers are orthogonal to the B field, and they experience no Zeeman splitting at all. But some are or have a parallel projection, and they have the splitting. And we see, okay, minus and plus 1 just simply splits with increasing B field. And we can also not only use this to sense, but also to lift the degeneracy and then address only the minus 1 state, for example, or plus 1 state if you want to. And now to the strain. So we have the normal strain only, no shear involved here in the NV center. And so we have axial strain and non-axial strain, and the Hamiltonian looks like this. So axial strain has finally the influence that we effectively shift the 2 sublevels here up with increasing axial strain. And the non-axial strain has 2 effects. So we have a splitting comparable to, so a splitting of ±1, as you see here, comparable to the Siemens splitting. And we have a mixing of those two states, which can sometimes be exploited for experiments, but in case of sensing, we don't take much care for that. We just look at the splitting, and then we see, okay, we have a certain axial strain or not. And yeah, if we just look at the eigenlevels then and make sure that we don't have any orthogonal B field, or at least only a very weak one, then it turns out that our frequencies, resonant frequencies of those states is the zero field splitting, the axial strain, and then below the square root, the non-axial transversal strain and the external field. And with the external field, we can tune whether we are able to sense the axial strain only, because the non-axial strain gets less important with increasing B field, and the square root is only a constant. Or if we make sure the B field, the external one, is very weak, of course, then the influence of the non-axial field gets more and more important. And then we are also able to separate between the influence of axial and non-axial strain, which you will see in a few slides. So here's just a measurement we did of shallow NV centers in diamonds. So we have a thin diamond membrane, and shallow means the NV centers are very close to the surface. So only 10 nanometers away from the surface, which means they experience a quite strong surface tension or stress. And you see the non-axial splitting here. So we are more or less, the center of mass is close to 2.87, so the axial strain is quite weak, but non-axial strain is quite strong. So that's just the intrinsic strain in the diamond, so no external strain applied. Okay, and now I want to come to the experiments. And I want to give you an overview of different kinds of experiments which performed beautiful measurements with respect to sensing of strain. So here we have a very high pressure experiment. So the group of Marcus Doherty from Melbourne, Australia, they put bulk NV center in a diamond anvil cell. And so they were able to generate extremely high pressure on the diamond. And they just looked, okay, what happens to the different spin levels and even the zero photon line. So one effect now due to this high axial strain is that the ground state ODMR shifts to higher frequencies as explained before. So the axial strain shifts the splitting or the plus minus sublevels. But in addition, since the strain is that high, he also influences the Coulomb interaction between the electronic or the unpaired electronic spin states. So effectively, the ground state and the excited state electronic configuration gets higher in energy, and you can really see this. So yeah, so this distance, so the zero photon line increases with energy, and you can see this now here in the measurement of the ZPL shift. So pressure increases to tens of gigapascal, and the position of this distance really increases linearly. And here's the first measurement explained. So you see that these spin sublevel splitting also shifts in the center of mass with higher pressures applied. So if we look at sensitivity as depending here on the ratio, so the change of, in this case, for example, the ODMR shift with respect to pressure. Then we have optical setup parameter just determined by our optical experiment, how good we collect finally the photons. And then, since we are in the quantum regime, T2 is important, so our coherence time of our spin or NVs, nitrogen vacancy centers. And in case of the ODMR shift, the resolution or the sensitivity is quite bad still. So it's only 600 kilopascal per square root hertz. And in case of the ZPL, especially if you go down to low temperatures, you can reach below 100 pascal per square root hertz. So that's already quite sensitive. But if we want now become even more sensitive, we can put a little more effort in the engineering of our sample. So here's something a group in Stuttgart by Jörg Wachtrup did. They didn't use just a big bulk sample of diamond, they used thin membranes. So here's a membrane of the thickness of 27 microns. And then they created even thinner parts by plasma etching. Here the thickness is only in the order of 1 micron. And then they implanted NV senders very close to the surface in ultra pure diamond and applied just pressure by nitrogen gas. And they were able to measure now the pressure in 2 different ways. One is just maybe first this picture here, just only the deflection of the membrane. So just by the pressure, in this case, for example, 40 Pascal, the membrane bends, so it's getting deflected, which means the NV senders shift out of focus of your laser spot. And you see, okay, the count rate decreases. And that's just illustrated here. So your membrane is that thin and that sensitive, yet you can measure really low pressure. And here they just did the measurement over different applied pressure to see how the deflection really changes. But parallel to that, so that's a very classical way to measure the pressure, of course. But here it's also possible to, again, measure the spin shift, the sublevel shift with the ODMR, as explained before. And you also see it's a very linear behavior. And the sensitivity turns out, in case of the deflection, it's very sensitive to single Pascal per square root hertz. And ODMR is way better now than in the experiment before. But so it's in the order of 100 Pascal per square root hertz. But interesting is that the applied pressure, or the range of the pressure you could apply, is very big. So you can go of several orders of magnitude. So the upper end is really when you break your diamond. And these membranes, although they have a thickness of only 1 micron, they are still very robust. And the maximum pressure they applied was 3 bar. And then they were scared it could break, but it was still quite nicely intact. So that's also a way how to sense uniaxial strain. So far, I only talked about uniaxial strain, and now I want to come to how to create 2-dimensional images of strain, of both axial strain and non-axial strain. And that's just some proof of principle experiment by the England group at the MIT. So what they used a polycrystalline diamond of tube type 2A, so a very pure diamond, but polycrystalline, so there are grains inside, and also the NV density changes from grain to grain. There are clusters. And also, in addition, there are regional preferential orientations of the NV. And what they did now, they performed a wide field imaging to create these beautiful fluorescent images. And you see here the bright spot is a cluster of NV centers, very bright. And here on the top right corner, you see a grain boundary. Luckily, these grain boundaries are also very fluorescently active. So you can see this in the same visible region, very bright. And now what they did, they created non-axial strain and axial strain maps. And to explain this, we just look at these 2 pixels here, and the blue one and the red one, for example. And you see now, in case of the blue one, where you are quite far away from this grain boundary, where we assume, okay, the axial and non-axial strain is quite weak, we see, okay, the center of mass is not shifted at all, so the axial strain is quite weak for the blue one, but there is a small splitting, but not very big. And in case of the red one, where the distance is way less to the grain boundary, we see, okay, the center of mass is shifted, so there's a lot of axial stress, and the splitting is also increased. And then they did this for all the single pixels and were able to really create these axial strain maps and non-axial strain maps. For example, as expected, the axial strain is, of course, extremely big in the grain region and then decreases, and the same for the non-axial stress. And then they were also able to do three-dimensional maps just by changing the focal spot size or depth, and could really investigate the influence of these grain boundaries. And the sense, so it's just basically amorphous carbon, and so due to this grain grow process, they made sure that this grain boundary exists. It's basically amorphous carbon. And that's also the reason why it's so fluorescently active, this amorphous carbon. So that's beautifully visible in the fluorescence regime. Yeah. And yeah, so it's really a nice experiment to see, okay, we can, by using these NV senders, create maps. And now you can think of different kind of applications to really exploit this experiment. If we, for example, say we want to deposit a specific film, antiferromagnetic, ferromagnetic, on top of diamond membranes, and then we could also be able to sense the strain by the volumetric change of our thin layers. That would be a nice application. And in the last few minutes, I think time's already up quite soon, I just want to go on some little bit different first. It's called enhanced NV spin state control, because with this strain we could also exploit the -1 +1 qubit, because minus and +1 qubit is magnetically forbidden because delta ms is equal 2 or ±2. So at least to directly drive it. But with strain it's possible. And we could do this by transversal AC stress coupled to both states. And there are different experiments, especially by McCreary and also Maletinsky group. And what they just created, a piezo electric actuator on top. Then that's the diamond with NV senders inside, and here below the objective, and an antenna for applying microwave fields. And once they hit with their resonator the frequency of the splitting, they were able to coherently drive, in this case Rabi oscillation, just with mechanics. So no B fields involved, only the mechanical drive of coherent spin state. And also they were possible to drive them in a Ramsey type of way. So these plus-minus qubits then really enriches your abilities for sensing, because this plus-minus state is insensitive to thermal fluctuations, which then would be nice for magnetometry when you are insensitive to thermal fluctuations. And then in the end, very quickly, I want to talk about these cantilevers, because you can think of many different kind of geometries you could design out of your diamond with NV sender inside to whatever application you have. Of course, you have the membranes, but you can think of the one-sided clamp cantilever or two-sided clamp beam and do measurements with those. So here, these cantilevers with extremely thin diamond are very good candidates for mechanical resonators and for sensing also, because they have a very high Q factor, so the damping is very low. If it's made out of pure diamond, the coherence time is very long, so it can exceed 1 millisecond, especially at low temperatures, but even at room temperatures, it can be very high. And at the base, of course, the strain is also very large. And here it's just an image where you see that the group here out of Basel, the Maletinsky group, what they did, they implemented NV senders here in the base, and we're also able to see those. And so it's just very quickly again sensing is these beams. So of course you see if you do the Euler-Bernoulli beam theory and simulate it, you see, okay, the highest strain is as expected in the base, and again this influences your splitting here. And if you sense it, you see, for example, in this case, the distance from the base is increasing, and as expected, since strain gets less and less, also the splitting decreases. And the black curve is just a theoretical prediction from Euler-Bernoulli theory, and that's just a proof that these are very sensitive. So here the sensitivities of these cantilevers is in the order of 3 to the power of -6 strain per square root hertz. So one strain is just a delta L over L, of course. So quite sensitive sensors. And I think since time is over already, I want to skip this. So it's just basically that with this cantilever, you can again coherently drive with the mechanical mode your spin system. Here's just a Hahn echo sequence. It looks a little bit messy, but it's just the first zero order Bessel function, because the phases are not matched. And here's also, if you include nuclear spins, you see that you could split again the sidebands with phonon interaction. But that's not that important for now for the sensing. It's just another application possibility. So to sum up, I quickly mentioned that the NV sender is a nice sensor for different kinds of fields, for magnetic fields, obviously, but also for electric fields, for temperature, and for strain. The sensitivity is very high, especially then for strain, when you put in more effort in the design and engineering of your samples. And there are different geometries possible, which allow you to, whatever you want to apply, can create even two-dimensional images with membranes, for example. And then you could, as an outlook, think of depositing metallic films on top, and then measure with shallow NVs below just the volumetric chains, in case you have a strong, for example, spin-lattice coupling, and to see how strain then affects your NV senders and measure this and create images. And of course, very quickly, I mentioned in the end this enhanced spin control, and that it's also possible to coherently strain and drive the spin with the strain of your resonator. Yeah, with that, I want to thank you for your attention.